This will be the first screencast for Physics 234B. We start with electric charge and electric forces. I know you've had a course on electricity and magnetism before, so some of this will be familiar to you already. But the important new thing in Physics 234 is to see how calculus is used in the theory of electricity and magnetism. So we're going to start with electric forces. So here's a little introduction. Electric charge is a property of matter. Any object may be electrically neutral or may be net positively charged or net negatively charged. And then like charges repel and unlike charges attract. So if we have two positive charges, two small objects, we could consider these to be particles, and they have the same sign of charge, so let's say they're both positive, then they repel each other. In other words, there's an interaction where each particle experiences a force directed away from the other particle. And by Newton's third law, the forces are equal but opposite. So this could be two positive charges or two negative charges, because like charges repel. On the other hand, if we had one positive charge and one negative charge, then the interaction is an attraction. The two objects would experience forces directed toward the other object. So unlike charges attract. Now this little diagram here shows the directions of the forces and indicates that Newton's third law is satisfied. The two forces in the interaction are equal but opposite. Now, what's the strength of the force? Before I write down the equation for the electric force, let's review a brief history of the science of electricity. Who discovered electricity? Well, we know the answer to that. It was a man named Thales, or Thales of Miletus. Miletus was the name of the city where he lived. He lived in the ancient civilization of Greece. Miletus is a city on the Mediterranean Sea, which is near Greece. Thales lived 624 to 548 BC. So we're talking about the very early history of science, hundreds of years ago, really thousands of years ago. Thales was the first scientist in Western civilization. And Thales observed that when amber is rubbed with wool, then it will attract certain lightweight objects like feathers or bits of straw. And he could see the attractive force as the electrified amber would attract these lightweight objects. Today we call this effect static electricity. And Thales wrote about this. He told other philosophers about this. And they wrote about his observations. So that's how we know that Thales discovered electricity. Now, another name in the history of electricity is William Gilbert. William Gilbert was an Englishman. He was a physicist and a scientist and also a physician, a doctor. He was the physician to the Queen of England, Queen Elizabeth of that day. He lived 1544 to 1603. And he wrote a large book, De Magnete, written in Latin, the first book about magnetism, where he showed that the Earth is a big magnet. But Gilbert also discovered that many materials, not just amber, can be electrified by rubbing with other materials, not just with wool. So amber rubbed with wool produces a certain effect, and many other materials can show that same effect. And he named the effect electricity. So that's where we get the word electricity in the English language. It was a word chosen by William Gilbert. He named it after the Greek word for amber. The Greek word for amber, written in Greek letters, is electron. And Gilbert, seeing that Thales was the first person to observe this effect, named it after the material amber. Now, moving a little further ahead in the history of electricity, Benjamin Franklin was the first American scientist. He lived 1706 to 1790. And Franklin invented the theory of positive and negative charge. Franklin invented the theory that different materials could have different kinds of charge, and some were positively charged and some were negatively charged. And like charges repel, unlike charges attract. Of course, Franklin is famous for the kite experiment, in which he showed that lightning is an electrical phenomenon. Now, living about the same time as Franklin, a little younger than Franklin, Charles Augustin de Coulomb was a French engineer and scientist. And Coulomb measured the force between charged objects. Coulomb lived 1736 to 1806. His life coincided partly with Franklin. He was a little younger than Franklin. And what Coulomb discovered is that the force between two charged objects is proportional to 1 over the square of the distance between them. So there's a universal constant K, and then there's the amount of charge on the first object multiplied by the amount of charge on the second object. That quantity divided by the distance between the two objects, divided by r squared, is the strength of the force on either of the two objects. So we have two objects, let's say two positive objects. They have equal but opposite forces. The directions are directed away from the other charge, and this distance is the distance r. The strength of these two forces is K, Q1, Q2 over r squared, where K is a universal constant. Now, in honor of Monsieur de Coulomb, the standard unit of charge is the Coulomb, abbreviated capital C. So you probably remember from your previous course on electricity and magnetism that C, or Coulomb, is the unit for electric charge. One more name in this history is J.J. Thomson. J.J. Thomson was an Englishman. He lived a bit later. He lived from 1856 to 1940. He did experiments in the late 19th century and the early 20th century. And he did the experiments that proved that electric charge is a property of subatomic particles. He discovered the particle we call today the electron, an elementary particle that occurs in all atoms. It's the negative charge in an atom. And every electron is identical to every other electron. Every electron has a certain charge, which we define as negative E. So E is a fundamental constant, and the electron charge is negative. That's coinciding with Franklin's definition of what objects would be considered positively charged and what objects would be considered negatively charged. Well, the electron is negatively charged. And all electrons are alike. Every electron has the same mass, call that m sub e. That fundamental charge, E, is 1.602 times 10 to the minus 19 coulombs. It's a very tiny number when expressed in the unit of the Coulomb, because electrons are very tiny. And the mass is 9.11 times 10 to the minus 31 kilograms. So when expressed in terms of engineering units like kilograms, it's a very tiny mass. So electrons are tiny subatomic particles. They occur in every atom. And that's the source of negative charge in the universe. Now, of course, every atom has a nucleus, and the nucleus is positively charged. And the electrons, which somehow move around the nucleus, are negatively charged. The fundamental charge in the nucleus is the proton. The proton has a charge plus E, exactly the opposite from the electron charge, opposite in sign, exactly the same magnitude as far as we can measure as the electron charge magnitude. Okay, so the electric force between spherical charges, think of these as small objects or particles, is given by Coulomb's law, measured by Coulomb. If we have let's say two spheres with charges Q1 and Q2, then the force on Q1 is K Q1 Q2 over R squared R hat, where R hat is the direction pointing away from the other charge, Q2. So we draw a vector. Let's call it R, which is the vector from Q2 to Q1. The direction of R is directed from Q2 towards Q1. And the length of the vector is the distance between the two objects. In the case of spheres, it's the distance between the two centers of the spheres. Or if these were tiny particles, it would just be the distance between the two particles. So the force magnitude is K Q1 Q2 over R squared. And the direction is the direction of R. So we write the force vector as KQ1 over R squared, R hat. R hat is a unit vector in the same direction as R. So R hat is in the same direction as R, but it has length 1. Whereas the length of R is the distance between the two charges, if they're spheres between the two centers. Of course, force has to be a vector. It has to have a direction. So we write it as a number times a direction vector, r hat. You should be in the habit, whenever you write a vector, as write the symbol with an arrow over it. For example, a force is a vector. So if you write F, that's not complete. You have to write F with an arrow over it to indicate that it's a vector. Now, in the case of unit vectors, instead of an arrow, we write a caret symbol or a hat symbol. That means it's a vector, but its length is equal to 1. All right, so that's the force on Q1. Now what about the force on Q2? Well, it has the same magnitude, so it's K Q1 Q2 over R squared, but it's in the opposite direction. So the direction vector is minus R hat. So it's minus K Q1 Q2 over R squared, R hat. And you have to be a little careful about the signs of vectors, because the vector has to have a direction, but is it in this direction or is it in the opposite direction? Well, those correspond to different signs. If I have a vector V, minus V has the same direction, the same magnitude, but the opposite direction. All right, so these could be small objects of any shape, really, as long as they're far enough apart. If they're far enough apart, it doesn't really matter what the shape is. These equations are valid for spheres, or more specifically, for spheres with uniform charge density. But these could be particles or spheres, just small objects of any shape, as long as they're far enough apart that the shape of the object is not affecting very much what you define as the distance between them. They have positions x1 and x2. So again, position is a vector. So Q1 here has a position x1. It has coordinates x1, y1, z1. So we have some origin, and we have Q1 over here. So there's Q1. And this is the vector x1. It's the position vector of Q1 relative to what we chose to be the origin. Now we have another charge over here, Q2. Well, it will have a position vector. There's x2. It's the vector which goes from the origin to the object that we're locating. So that's x2. Now what's r? We have two vectors actually. We have the position vector for Q1, we have the position vector for Q2, but the force depends on a third vector, r. What's r? R is this vector. R is the vector from Q2 to Q1, the way I defined it. So R is x1 minus x2. Because if I take x2 plus r, I get x1. So if I move this to the other side of the equation, x2 plus r is equal to x1. So here's r. Or in terms of coordinates, r has coordinates x1 minus x2, y1 minus y2, z1 minus z2. So geometrically, r is the vector from Q1 to Q2. Or algebraically, it has three components, which are x1 minus x2, y1 minus y2, z1 minus z2. Well, that's r vector. Now, what appears in this equation is r hat and r. What's meant by r is the distance between q1 and q2. When I write r with no vector sign on it, no arrow on it, then it's not a vector. It's just a distance. It's just a length. So the position vector, or the relative position vector, is r hat. It has magnitude r, that's the distance between the two charges, and direction r hat. That's the unit vector pointing in the direction from q2 to q1. Or another way to say it is r hat, divide both sides of the equation by r hat is r vector divided by r. And what appears in the force formula is r hat divided by r squared. R hat is r vector divided by r. So that's the same as r vector divided by r cubed. We call this an inverse square law because the strength is proportional to 1 over r squared. But if we want to write it out as a vector, actually the best way to write it, and the way which makes it possible to do the calculations in the homework, is to write r hat divided by r squared is r vector divided by r cubed. Why is that convenient? Well, because r vector, it can be immediately written down in terms of the coordinates. So when it comes time to do the homework problems, think about writing this as k q1 q2 r vector divided by r cubed. That doesn't mean it's an inverse cube law, because r vector has a power of r in it. So it's an inverse square law as far as the magnitude is concerned. Now, what's r? The distance from q2 to q1? Well, by the Pythagorean theorem, r squared is x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. You know, it's easy enough to see that in 2 dimensions. If we had a distance x1 here and a distance y, or let's call it y here. Suppose we have x here and y here. This is r. Well, if I look at this little right triangle here, r squared is the hypotenuse. The square of the hypotenuse is the square of the two sides, y squared plus x squared. So in 2 dimensions, r squared is x squared plus y squared. Well, in 3 dimensions, it's x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared. Well, that completes the theory of the electric force. Well, there's a little more to say than that. That's just the force between 2 point-like charges. Q1, we'll often use Q to stand for charge, so Q1 and Q2, and a distance r. But what if we had many charges? What if we had another charge, Q3? Then what would be the charge on, let's say, Q2? Well, there would be a charge exerted by Q1, and I would have to add a charge exerted by Q3. So I would add those 2 force vectors as vectors. Or suppose I had an object with some shape. Maybe it's shaped like a peanut. Maybe it has charge Q. Well, that will also exert a force on any of these little point charges. What's the force exerted by this charged object, which is not so far away that I can ignore its finite size? Well, that will be part of part 2 of the screencast, examples. So watch part 2 of the screencast, to get some hints on how to do the Lon Kappa problems.